Guess who's using a different camera? I am. Yay! Anyway, today I'm going to be... Look at all this space I have. This is amazing. Solid structures. But A-level. Which means it's more fun. Because I actually enjoy chemistry, which is why I took it. It'd be a bit sad if I took chemistry without liking it. Anyways. So first it starts off. We start off with ionic solids, right? The examples they give you are sodium chloride and cesium chloride. What you basically need to know is, from GCSE, if you remember, they form crystal lattices, which look a little bit like that. Yeah, that's basically what they look like. And the way that ionic structures want to arrange themselves is minimize the electrostatic attraction, maximize the electrostatic attraction and minimize repulsion. Because, they want to be in a place that's comfortable for them. They want the least amount of energy for where they are. So it's easier to be in a place where, if you think about people, it takes more energy to be around people that you don't like. But it takes less energy to be around people that you are like, and being away from people you don't like. Which is why they maximize electrostatic attraction and minimize repulsion. And that is the reason why any compound forms the shape it does. That comes in a different topic. But anyway, this is solid structures. So what you need to know for these solid structures is that the coordination numbers, first of all, if you have the coordination number of, say, sodium in sodium chloride, if you look at sodium, which is the cation, it's a bit blurry, isn't it? I've moved it a bit closer, hopefully it's easier to see. Do it a bit bigger. Sodium, the cation, which is a positive ion. Anions are negative. I remember it by cation. Sort of has the same cat in it. And cats are nice and friendly, if you like cats. Anions makes me think of onions. And onions are smelly. And therefore bad. So, anions, negative, cations, positive. So, sodium would be the cation, and Cl would be the anion, and in this case, the anion is larger than the cation. Usually that is how it is. If you were asked, I'll draw a little example. So, sodium you have here, and around it you have 1, 2, 3, 4, that's going forward, 5, 6 chlorines. Just do bigger circles. So that's going up, down, left, right, forward, back. So 6 chlorines around the one sodium. So if they were to ask you the coordination number of sodium, you would give 6. Same for chlorine, because chlorine has the same thing going on. So then the coordination number of chlorine would also be 6. So that means the crystal coordination number, which is of the whole crystal itself, would be 6:6. That's how you work it out, basically. Now, you can get asked to draw the unit cell of it, which would just be this tiny bit, rather than the whole thing. Although they can ask you to draw this whole thing. So, watch out. And generally, the cation is smaller than the anion. Although, in the case of cesium chloride, the cesium is the cation, and it is larger than the anion, rather than smaller. And because of that, it can fit more chloride ions around it, because it's a big ion. So rather than just having 1, 2, 3, 4, 5, 6, up, down, all around, it has 1, 2, 3, 4, 5, 6, 7, 8 in a little cube shape around it. Haven't really done it in the center, but you know, pretend that's by there. It's, oh gosh, it is in the center of this cube shape. And that would mean if you got asked the coordination number of cesium, it would be 8, sorry, not 6, 8. And if you got asked the coordination number of the chlorine, it would also be 8. Okay, it's chloride, I suppose. So then the crystal coordination number would be 8, 8, rather than, well, 6, 6 in the case of sodium chloride it was. So you just look at how many, if they give you like a diagram, it's of other examples, it's going to be just expanding upon what you already know. Oh, whoops, I'm hitting cans. So they would probably ask you things about other molecules that look similar. So if it's this sort of shape, this is a better diagram. That sort of shape, it would be 8, 8. If it's the other sort of shape, that would be 6, 6. Now, you cannot... This is the whole lattice. It is very complicated. This is really blurry. Wow, it's like it has... my camera needs glasses. Anyway. This is just a unit cell. I don't think they'll give you a question on this. Because look how complicated it is. Hopefully not, but if they do, you know. Well, you just connect this to each of the things, I'm pretty sure. That's what it seems like. You just do it by 4x4, like squares. You can do 4 squares there, 4 squares there. Yeah. Now, physical properties of ionic structures. They do have high melting and boiling points because, you know, you have ions. So, you know, positive, negative, opposites attract, which means there are strong electrostatic forces of attraction. You need to remember to say electrostatic, because if you miss out words, a lot of the time in mark schemes, they tend to just, I don't know, you lose marks if you're not specific enough. You need to tell them everything you can about the subject, even if it's really obvious. But, you know, strong electrostatic forces of attraction between oppositely charged ions, and that would mean it requires a lot of heat energy to break, so that's why they have high melting and boiling points. Now, they're also brittle, because if you have... If I add in... Oh, I've done these really big. If you have, you know, sodium chloride. Oh, whoops. Sodium chloride. And then you have chloride, sodium. Chloride, sodium. That's usually how it's laid out. In little rows where everything's all perfect and opposite charges are next to each other. If you were to apply a force to that, the layers would move. So say we move the middle one, right? You have the outside ones. And if you were to move the middle layer to the right, that sodium would move right one, that chlorine would move right one, so that sodium would in fact be next to these sodiums, and that chlorine would be next to these chlorides, sorry. And that is bad, because now you have ions of like charges next to each other, so they would repel, and that would mean that the crystal lattice would fracture, which is why ionic crystal lattices are brittle, rather than being malleable or ductile like metals are. Now, they also, if they're in their little crystal lattice shape, I'm going to do a better diagram than that. Oh my gosh. Didn't really do that one very well, did I? If they're in the little crystal lattice structure, they're all sort of, it's not very good either, they're all sort of together in, they're fixed in place, you know, they're solid, they're fixed in place, they're not able, none of the ions or electrons are able to move around the place. Well, there's no electrons, is there? There's just ions. None of the ions are able to move around the place. So that is why it cannot conduct electricity. However, if this is dissolved in water or whatever, any other polar liquid, I suppose. If it's dissolved in water, though, usually you say, or if it's molten, then the ions can move around and sort of knock into each other, and that is why electricity can be passed on through the liquid. Yeah, if they're aqueous, if they're within a liquid or a liquid themselves, then they can conduct electricity. And the reason why they are able to be solutes is because they're polar. Water itself has delta positive and delta negative charges, which means that is a polar molecule, and this would also be polar. You know, different ions of different charges right next to each other. Opposite charges right next to each other, so that would also be polar. And like dissolves like, so that's why they can dissolve in water. Yeah. Now you have some examples of this. You have diamond and graphite. These are both made of carbon-to-carbon bonds all around the place. You will want to draw the tetrahedral structure in diamonds, which is just 1, 2, like that. Oh, I haven't done that very well. I haven't done that well at all, actually. It's this part of the shape. 1, 2, 3, 4, 5. They should, again, I think they're probably just going to ask you to draw little things, but sometimes they can ask you to draw larger structures, which can be annoying, but, you know. It's all uniform throughout. It's all loads and loads and loads of covalent bonds throughout the whole thing, which are all connected. Covalent bonds are inherently strong, so obviously it takes a lot of heat energy to break them, especially if they're in every single direction. So it's like uniform strong bonds all around each carbon, which makes it have a really high melting point, as you know with diamonds. Ooh. Yeah. Graphite is still a covalent bond, but it's different. There's only 3 covalent bonds with each carbon atom. Usually you have 4. Usually carbons are bonded to 4 other things, but in graphite it is just 3 other ones. Ooh. And that would be connected to that and that. Oh wait, no. That would be... oh, I've done it wrong. Okay, I've done a bit more of an accurate diagram now. A bit messy, but you know. This 1, 2, 3. That shows they're connected to 3 other ones, which means that they are able to form other bonds as well. So within each layer of your little carbon, you have these van der Waals forming, which are they're very weak. Van der Waals bonds are very, very weak. They don't require much heat energy to break whatsoever, so these layers within themselves are strong, but between them, those are some weak bonds. So that means that the layers can very easily slide over each other, which is why pencils do what they do. Graphite and pencils, you do that. That's just the layers of pencil. That's the layer of graphite in the pencil sliding over the other one, which means it's very soft. And yeah. Wow. Yeah, and also, because one of the carbons aren't bonded, there's only 3. One of the valence electrons. Valence just means related to a bond. You know, related to an electron being bonded. one of the valence electrons, one of the electrons that should be bonded to something, isn't, which means they just sort of are delocalized and can move around the place, which means they can conduct electricity. Wow. Amazing. Diamonds don't have free electrons because they have carbon bonds, 4 carbon bonds for each carbon, so there's no free delocalized electrons that can move and carry charge. Yeah, that's sort of it. They're both strong melting points because the covalent bonds require a lot of heat energy to break in both the structures. It's just diamonds are harder because strong covalent bonds in all directions between each carbon atom, and these are soft because the van der Waals between the layers of carbon are very easily broken, so they can just slide around the place very easily. Yeah, simple molecular bonds, such as iodine is an example you're given, because it is one of the diatomic molecules. It's just I2, so it's I to I, which is low melting and boiling point, because intermolecular forces, I believe it was. Yeah, intramolecular bonds are within the molecule. Intra means within. Inter are between the molecules, because inter means between. Sometimes it's a bit hard to remember that because they're very similar prefixes, but intra is within, inter is between, and it's the intermolecular bonds that affect the physical states of the, well, in this case it's not an atom, it's what's it called? A compound. Between the compounds. Yeah, because they're really, really weak, because they don't exactly have any hydrogen bonds. It's just van der Waals forces, which are weak. It doesn't require much heat energy to break them. So they're low melting and boiling points, and they're soft as well because of that. There's not really any. It's not really soluble in water, is it? It's not a polar thing whatsoever. The electronegativities of these iodine things are the exact same, because it's the exact same atom. If you don't know, electronegativity is basically the tendency of which an atom within a covalent bond attracts a shared pair of electrons towards itself. So it's just how likely it will pull the electrons towards itself. And if in the case of water, oxygen, higher electronegativity, it pulls the electrons within the covalent bond towards itself more than the hydrogen does, which is why it has a delta negative charge and the hydrogen has a delta positive charge. That is a polar molecule because there's a difference in the charges of each of the things, but this is the exact same. There's no difference in electronegativity, there's no delta positive, delta negative charges within the covalent bond. So they're not the same. Like dissolves like, and these are not like, so it's not soluble in water. And it's not very good at conducting electricity either, because there's no delocalized electrons in this to move and carry charge, because all of them are being used in this bond. So there's nothing really good going for these iodine molecules at all. Now, you also need to know about ice. In ice, because it's water, there's nice hydrogen bonds, because, well, there's hydrogen, isn't there? So these have 2 lone pairs of electrons, and if you get another molecule, then the delta positive, hydrogen, would be attracted to the delta negative lone pair of electrons, the lone pair of electrons on the delta negative oxygen. So yeah, and then it just sort of continues like that through the whole molecule, through the whole liquid, I guess. This is the molecule, these are between the molecules. So the intermolecular bonds are hydrogen, which are strong intermolecular bonds. not as strong as intramolecular bonds, but stronger than van der Waals, which are another type of intermolecular bonds, which means that it has a higher melting point than, like, well, iodine. Specifically in ice, because it is... The reason why ice is less dense than water and therefore floats on water is because the way it's held is... In a solid, water is held in a very open tetrahedral shape, you can see here, and it's just fixed in that position, which means there's lots of little pockets of air. So the molecules are less densely packed together, because they can't really... You can't have anything going like that, you know? That is a bit more dense than if it was just held open like this. So that's why ice is less dense than water. And yeah. They also want you to know, they let you know strong bonds within the water molecules are polar covalent, which just means there's, within the molecule, the intramolecular bonds are, well, covalent bonds, and they're polar because there's different charges. Polar opposite charges. So, yes, polar covalent bonds within the water molecules. Intra. They do want you to know how to draw a water molecule bonding to 4 others, which is not really too difficult. I'm going to get a new page to do this, because this is going to be a bit big. So if you have your one water molecule... Have I been doing this? I've been doing HO2 this whole time. It's actually H2O, sorry. 2 hydrogens, 1 oxygen, and that pairs like that. And these, ignore the little dots by here. These dots are meant to be there, they're not. Alright, this is actually how you draw oxygen molecules. 2 hydrogens, 1 oxygen. And then it can bond to 4 others because there's 1, 2 lone pairs of electrons on the oxygen and 1, 2 hydrogens. So these would bond to the... oh gosh. Yeah, that's fine. To an oxygen in another molecule. I'm not drawing all of the delta signs, but you would have to draw all the delta signs. These would bond to another oxygen lone pair in a water molecule. And then this one would bond to a hydrogen in a water molecule. And this one would also bond to a hydrogen, because there's 2 lone pairs of electrons, that one would also bond to a hydrogen molecule. And yeah, that's basically how you draw it. You just make sure to draw all of the delta positive and delta negative signs and all the lone pairs on each of the oxygens. Now, physical properties of ice, as I said, well, they don't put this... it doesn't come up terribly often, I don't think. They haven't at least put it in the table in my book. So, they say it, like, offhandedly. But I would note that, you know, as you know, ice is less dense than water, so it floats on water, which can be good for, like, aquatic habitats. If the ice sunk to the bottom, it'd be squishing a bunch of fish. And anyway, it's a good... if you have a bunch of fish and it's really cold out there, it just keeps this water warm. So, just keep that in mind. And you also need to know low melting and boiling points, because... well, hydrogen bonds don't actually... compared to van der Waals, they require more heat energy to break, but not as much as other bonds. Like diamonds, the only bonds that they had were intramolecular, and intramolecular bonds between, like, within the molecule are always stronger than intermolecular bonds, which are between molecules. So ice does have low melting and boiling points, because the hydrogen bonds don't require, comparatively, a lot of heat energy to break. And electric conductivity is also poor in water, in pure water, sorry, because in pure water there's no ions floating around the place. However, Well, yeah. I'll just use this water. I'll cross that out because it makes it just a bit messy. There's not many... It's just water in there. There's nothing free moving around. Everything's already bonded to each other. However, if there's ions in the water dissolved, so you have like... I'll just do... I won't put any of the delta negative signs or anything. So you have your water, and say you have sodium dissolved in it. That is going to be moving around all the time. These can move wherever they want to within this liquid. So that would conduct electricity. If you have more, let's put an iodine in there, why not? So, wait 1 second. I'm just checking my periodic table. I didn't want to give it the wrong charge, but you know, have iodine as well, or chlorine, or magnesium. If you have ions floating around, there's loads of ions in this now. They would be knocking into everything and, you know, conducting loads of electricity. If there's nothing, if there's no ions whatsoever, then it doesn't conduct electricity whatsoever. So if you talk about the conductivity of water, if you're saying it doesn't conduct, specify pure water, and then also say if it has ions in it, it can conduct, and the more ions it has in it, the more conductive it is. Yeah. And then there's also, briefly mentions metallic bonding. Metallic bonding isn't... It's not terribly difficult, really. It is just... You have a bunch of metal cations all in a lovely little row like this. So it's metal cations embedded in the sea of delocalized electrons. So that's your little sea. They like calling it a sea because it moves around, I guess. Of delocalized as well, because they're not in a specific one. They're not in one place. They're not static. They're delocalized. So it's metal cations embedded in a sea of delocalized electrons. And it's very strong because the electrostatic forces of attraction between these positively charged cations and negatively charged electrons, not ions. You can easily get confused with ionic bonding and automatically be like, oh, the electrostatic forces of attraction between the cations and anions. It's like, there are no anions in this. It is just electrons. Because it is just one metal. It is just magnesium. It is not magnesium chloride. So it is cations and electrons. And because, you know, oppositely charged, opposites attract. And, yeah. Metallic bonds are classed as intramolecular because it is within the molecule. This is the molecule. It's not different molecules. This is the entire molecule. So it's just the charges, the bonds, but inside of the molecule, which holds it together. Temperature increases if, say this is sodium, right? It is just a +1 charge. If you move up to magnesium, which is a +2 charge, then the charge on the protons increases. That is a massive proton. Not proton. Cation. That is a massive cation. Anyway, you know, you have 8 cations here. You therefore have 8 electrons. Here you have 6 cations. Instead of having 6 electrons, you have 12, because it goes off of the charge of the cation. And because there's a greater number of electrons in the sea of electrons and a stronger charge on the cation, it means that it's like the bonds are stronger, the electrostatic forces of attraction are stronger, so there's a higher melting point. Yay! Which is, you have to know about Melting and boiling points and hardness increase across a period with an increase in valence electrons, which is just outer electrons, because there are greater attractions between cations and the number of delocalized electrons which require more heat energy to break. So it's just if you go across a period, like my example, from sodium to magnesium, then the charges increase, so the electrostatic forces of attraction increase, and also there's more electrons, so therefore more heat energy required to break. Electrical conductivity also increases across a period because there's more valence electrons. Yeah, more electrons are able to freely move around the place. So obviously there's more stuff to move around to carry that lovely electricity. And that is all of that topic. Oh no. I'm knocking cans over again. I've done that twice today. Anyway, yeah. Bye!